Hello everyone, my project topic is an asymptotically compatible probabilistic collocation method for randomly heterogeneous nonlocal problems. This is a project I did with Xiaoshan Tian, Xu Yang, Xinjie Li, Clayton Webster, and Yue Yu. So our motivation comes from researches about randomness heterogeneous aerodynamics. Sometimes the nonlocal model without randomness fails to capture the correct property of the material. So we could add a random variable into the traditional nonlocal models. Our main contributions in this project include the design of an asymptotically compatible technique that provides accurate estimation for mean and standard variation of the solution of this kind of nonlocal problems, and rigorous mathematical analysis demonstrating asymptotic compatibility of the proposed approach. We also provide the numerical verification of this method on 2D stochastic nonlocal diffusion problems. We obtained first-order convergence to the nonlocal solution, second-order convergence to the local limit, and exponential convergence in parametric space. In the real-world application, with the KL expansion to represent the diffusivity coefficient, we provided an effective numerical procedure for solving the randomly heterogeneous nonlocal problems. First, let's take a look at the deterministic problems. We are considering a family of nonlocal elliptic equation with diffusivity A on the bounded Lipschitz domain. The equation you can see in the equation 1. The delta here means the radius of the compactly support of this kernel A, or the diffusivity, which is also referred to as the horizon. The equation A could be viewed as the nonlocal approximation of the traditional local PDE, which is listed as equation 2 here. In our validation, we use mesh-free quadrature rule to solve this kind of problem. We seek for a quadrature rule for function f with the following form. By solving the local optimization problem 3, quadrature weights may be obtained by solving this problem. Next, we'll show one of our first main theorem, the convergence for the mesh-free method on deterministic diffusion problems. We use U delta H here to represent the numerical solution of our technique. And we use U delta here to denote the analytical solution of the nonlocal elliptic equation, which is the equation 1 in this poster, and denote U0 as the analytical solution of the local elliptic equation, which is equation 2 in this poster. And the convergence of the arrow could be illustrated by equation 4 and 5. The error between the numerical solution of a method and the analytical solution of the nonlocal solution follows a first-order convergence as the mesh size h goes to 0. And the error between the numerical solution of our technique and that of the local one follows a second-order convergence as the delta goes to 0. Here, we assume that the quotient of delta and h is a constant. So you can also say this term goes to 0, follows a second-order convergence as the mesh size h goes to 0. After adding a random variable into the nonlocal problem, the diffusion problem becomes the diffusion problem with randomly heterogeneous coefficient. The diffusion coefficient A here should satisfy at least the 4 properties listed here. The most important one is the property 2, which told us that A could be applied eigenvalue decomposition and A could be represent in form in this kind of form. And A should also follows the symmetry and uniform ellipticity assumption. The general procedure of PCM is also introduced here. Step 1, generate collocation points as independent random inputs based on a quadrature rule, quadrature formula, such as we could use Chebyshev nodes or Gauss quadrature points. Step 2, at each collocation points, we use these collocation points in equation 1. So the equation 1 becomes a deterministic problem, which could be solved by some existing method, such as the one that we used in our project, the optimization-based quadrature rule. Step 3, evaluate solution statistics using the quadrature rule in step 1. The quadrature weights here, theta k here, is just the one that we get from step 1. Using formula 7 and formula 8, we can calculate the mean and standard variation of the solution. Here we present our next main theorem, the convergence theorems. Given m is a nature number as the number of collocation points in each random dimension, then for each semi-discrete solution U delta H, we define U delta MH as the fully discretized solution from mesh-free discretization and PCM. We define S delta D as the non-local energy space as follows. Then we have the following estimate. Theorem 2 told us the convergence of PCM method. Given the finite dimension subspace V and define U delta H as the projection of U delta in this space, then the error between the U delta H MH and U delta follows the exponential convergence as the number of collocation points M grows. And theorem 3 illustrates the convergence of the full discretization method, which told us that if we let this delta, the horizon delta goes to 0, the mesh size H goes to 0, and the number of collocation points M goes to infinity, then the solution of our technique convergence in both spatial space, physical space, and parametric space to the real solution of equation 2. We use the following 3 settings for test. In example 1, we test the convergence to the non-local solution. So in equation 1, we let the diffusivity A has the following form. Then we compare the numerical solution with the local analytical solution, Ux equal to cosine X and sine Y. In example 2, and example 3, we test the convergence of the local solution. First, in example 2, we let the right-hand side fx equal to 1 in equation 2, and the diffusion coefficient A has the following form with parameter k equal to 2 and a0 equal to 3. In example 3, we still use the right-hand side fx equal to 1. However, this time we use a given covariance kernel k, and we can use KL decomposition to derive of eigenvalue and eigenfunction form of this diffusivity A, which we will be using our asymptotically compatible mesh probabilistic collocation method. Figure 1 and Figure 2 shows the validation of our convergence theorem. In Figure 1, from left to right, shows the result of example 1, example 2, and example 3. In the left one of Figure 1 shows the convergence of discretization in physical domain of mean and standard variation, the error of mean and standard variation for 4 kinds of distribution. The uniform distribution, the Gaussian distribution, the log normal distribution, and Weibull distribution. The numerical results show illustrate that both the mean and standard variation, both the error of mean and standard variation follows a first order convergence to the non-local analytical solution. The middle one illustrates a second order convergence for the error of mean and standard variation to the local analytical solution. And the right one of the figure one shows the same trend as the middle figure, which is also a second order convergence in the physical domain to the local analytical solution. Figure 2 shows the convergence of discretization in the parametric domain. The same as before, the left figure demonstrates the exponential convergence in parametric domain as the number of samples grows up. Both the error of mean and standard variation are validated here, and 4 kinds of distributions are tested. The middle one shows the convergence, shows the exponential convergence of the PCM method for example 2. And the blue line and the orange line shows the exponential convergence, which is also compared to the yellow line and the purple line, which demonstrate a half order convergence of the traditional Monte Carlo method. In the right one of figure 2, this one also shows the same trend as the middle one. The exponential convergence for PCM method and a half order convergence for the traditional Monte Carlo method. So that's it. This is the presentation of our project. Thanks for listening.